13.73, we got a bucket and it's hanging from a spring. So we've got, let's draw that. So we've got a spring here hanging down. Connected to it is a bucket. Okay. And there's water leaking out of the bucket. Okay. So the water is leaking out. Okay. And that's happening at 2 grams a second. And we know, and other than that stuff, so they want us to first, when the bucket's half full, they want us to find out what the rate at which it is. So let's make that bucket half full of water. And normally wouldn't be able to see this because the bucket would be full, or bucket would be, would be opaque. But okay, so it's half full. Okay. And they ask us what's the period. Well, again, it's going to be just a mass on a spring, so we can use a T equal Part B of this problem really is the harder part, the part where you actually have to find the rate at which it happens. So you're going to take the derivative of the period with respect to time, which means you're going to take the derivative of that whole expression, 2 pi, come on, nope, m over k. Okay. Well, that actually is in some ways easier than you think. Some of these things aren't going to stand up to taking a derivative. This thing here you can't take the derivative of. It doesn't change. This thing doesn't change. The only thing that does change is this. But you can see it's going to be harder than you think. Okay, so let's factor all that stuff away. So we have d derivative of the period with respect to time. It's just going to be, remember, take the 2 pi and the root k and put them out front. I'm going to take the derivative of just that piece. But in order to do that, we're going to have to do some implicit differentiation, okay? Which means we're going to have to differentiate this and multiply it by the rate at which it changes. So that's going to be equal to 2 pi over k. The derivative of this piece, which would just be, it's m1/2, so it'd be 1/2 m to the negative 1/2. Okay, well, that's great, but we have to multiply it times the change in the change in the mass times with respect to time. It's only we can take the derivative of that. Okay. Those terms actually collect out pretty nice together because this is just 1 over root m, so it'll pop right into this little fraction pretty nicely. So it's going to be equal to, and this is going to divide out with that. So we're left with pi over root mk times dm dt, which seems like it'd be a problem, except for the fact that they already told you what that was. They told you it's like, what, 2 grams a second, and it is a negative change. So it's going to be just pi over the mass. Remember, the mass at the time is 7 kilograms. We figured that out earlier. 7 kilograms times 125 newtons per meter times, we have to change that to 0.002 kilograms per second. Again, we can't use 2 grams per second, okay, because it's going to be, because it has to match up with the kilograms over here, and it has to be negative. Okay. If we do all of that, we end up with negative, I'm going to put it over here, negative 2.12 times 10 to the negative 4th. And what's interesting about the units is that if you look here, we have kilograms times newtons over meters. That's actually kilograms times kilograms meters per second squared. So that's kilograms times kilograms over second squared, which means we have kilograms per second when we take the square root. So kilograms per second divided by kilograms per second leaves with no units at all. Okay, and that's actually okay because this would be seconds per second would be the derivative of the period with respect to time. So we should get no units. That actually works out okay. Weird, but okay. And it's a pretty small change in time. If you think about it, that makes sense too. For part C, I'm going to redraw that picture again. Okay, here's our spring. Here's our bucket. Yeah, not a great bucket. They ask what's the shortest period the system can have. Well, water is leaking out of that bucket at the bottom, remember, but it'll stop leaking when all the water is gone. So this 10 kilograms up here is going to be 0. All we're going to be left with is this 2 kilogram bucket that we have at the top. So our shortest period is going to happen when we have no mass of water and all mass of bucket, and that's going to be 2 kilograms over 125 newtons per meter. And again, that's going to give me 0.794 seconds when I put it in my calculator. So, and it is smaller. It makes sense. We have less mass at the top. Our spring constant stayed the same, so we should end up with a smaller period overall. We saw it was shrinking in our change in period over change in time, so we should end up with a smaller period overall.